In previous presentations, we've discussed the meaning of soil pH, how it affects the availability of particular nutrients, and in this third presentation, I'd like to provide some information about liming and how you deploy it within your farming system. One way to consider the approach to liming is to look at it in terms of the 4R approach, which really relates to the 4 rights, that is, identify the right lime source, apply it at the right lime rate, supply it at the right time, and placed or located in the right place. And that all fits it together and it operates within a farming system. The first part of this 4R approach to liming is to understand what the source of material is that we are using. So lime's calcium carbonate. It's not a fertiliser, it's a soil ameliorant. It does have some nutrients in it, calcium and magnesium, but essentially it's used to change soil pH. Liming materials are either ground limestone, which is calcium carbonate, or ground dolomite, which is a mixture of calcium and magnesium carbonates. The calcium and magnesium from those products doesn't play a role in soil pH change. They are what we call spectator ions. It's the bicarbonate that does the work in this situation, and what it does, it reacts with the hydrogen ions that are in the soil or in the soil solution, converting to carbonic acid, which then quite quickly dissociates to water and carbon dioxide. Lime has low solubility, and its solubility decreases significantly as pH rises. Above pH 9, the solubility will be about 1/20th of the solubility at pH 7. So at pH 9, lime is essentially insoluble. It usually requires incorporation to react with a soil volume, simply because of its low solubility. Lime doesn't move quickly and easily down the profile. It also takes some time for the lime to dissolve and dissociate to carbonate. That'll depend on soil pH, and it may not dissolve or dissociate at high pHs. And at high pH, it can also act to trap any exchangeable calcium in the soil. Just as we know that oils ain't oils, limes aren't limes. There's quite a variation in the quality of lime, and that's determined and expressed in its neutralising value. That is, its capacity to capture and neutralise those hydrogen ions. Pure calcium carbonate has a neutralising value of 100. Agricultural lime is then indexed against pure calcium carbonate, so the value will depend on the purity of the product and also the size of the particles. The top right graph here shows the equivalent rate in tonnes per hectare for different neutralising values of lime. For example, applying 1.7 tonne per hectare of lime with a neutralising value of 60 would give the same pH change as using 1.1 tonne per hectare of lime with a neutralising value of 90. Similarly, the size of particles can affect efficiency, with coarser particles being less effective than finer particles. Dolomitic limestone, which is often 28% magnesium, can have a higher neutralising value than limestone, simply because of the difference in molecular weights between calcium and the magnesium. Lime is given grades, and grade 1 lime has an equivalent neutralising value of 80 or better, and to be considered as lime, any materials need to have an equivalent neutralising value greater than 50. The quality of ag lime is not always apparent from its visual appearance. These are some examples taken from the Corangamite Catchment Management Authority's website. They show some of the limes and their equivalent neutralising value, as well as their neutralising value and the cost per equivalent neutralising value. The equivalent neutralising value, ENV, factors in both the neutralising value and the particle size, providing an index on how much acidity the lime will neutralise in the soil. In the example on the right, lime B has the same NV but is more expensive per tonne than lime A. The smaller particle size of lime B gives it a higher ENV, and so it turns out to be the cheaper lime source based on effectiveness. So when you buy lime, just make sure it comes with a test certificate explaining what its neutralising and equivalent neutralising values are, so you can work out what gives you the best value for your dollar spent on lime. What lime does in the soil is to neutralise the hydrogen ions that would be present on the clay or the organic particles in the soil. Essentially, the calcium carbonate dissociates into calcium ions and carbonate ions. And those carbonate ions then react with the hydrogen ions and produce water and carbon dioxide, which then disappears. And then the calcium ions move to reside on the clay particles, so that the particle is now stable and becomes a calcium-dominated clay rather than a hydrogen-dominated clay. The second of the R's is what's the right rate of lime? Well, it varies dramatically from soil to soil. What we're aiming to do is to increase the pH to 5.2, and that might take 2 or 3 years of lime application to slowly bring that up, particularly if the soil pH is very low. The amount of pure lime required is the pH change needed divided by the soil factor. The soil factor varies with soil texture, and it takes more lime to change a clay than to change a sand, so we have to account for soil texture. We also have to adjust for soil organic carbon levels. If the soil organic carbon is above about 1.2%, we'd need an extra 0.4 tonne per hectare of lime. We'd also need to adjust for the neutralising value of the materials as we've just discussed. So for example, with a soil of pH 4.7, if we wanted to raise that to 5.2 on a sandy loam soil with a 0.8% organic carbon, that might take 1.2 tonnes of lime per hectare in the top 10 centimetres. I think the key point is to understand that the required rate is driven largely by the specific target pH. The third of these 4 rights is the right place for lime. Where do we actually put it out across the field? Lime application is an excellent platform for variable rate application. And I've taken some examples from a paddock at Como Farms. They've done a grid sample of pH and produced a simplified pH map with areas in red from 4.5 to 4.8, in yellow from 4.8 to 5.2, and an area in the aqua and blue that are 5.2 and 6.8. We can look at where the lime would go if we wanted to get the whole of that paddock to 5.2. And basically we'd need 2 tonne per hectare of lime in the pale green areas, 1.5 tonne in the lime green areas, and about a tonne per hectare in the aqua areas. And obviously in the blue areas, because it's already at 6.5, we wouldn't be applying any lime at all. If we wanted to move that paddock to pH 5.5, because of the nature of pH, remember that it's a log scale, to get that extra 0.3 would require effectively twice the amount of lime required compared to moving it to 5.2. So we might be content with getting it to 5.2 with that 65 tonne of lime on the paddock. One of the areas that's important to make sure of is that when you're sampling, you do it correctly, taking care to account for stock camps, any old windrows, areas that might have missed spreading or highly producing areas. These are all likely to contribute to the variation across the field with pH. The fourth of the 4 R's is to determine what's the right time to apply lime. Typically it's in the early autumn, and that's because the dry conditions will enable the material to be spread more easily, and that paddock trafficability is usually good. It's also before seeding, and so that gives the lime some time to react and gives some neutralising value of any soil acidity before the next crops are sown. Just a point here that applying lime too close to seeding can tie up boron, and it's fresh lime that reacts with soil boron, and if boron's low already in the soil, that can be an issue. Some lime incorporation is good, and incorporation by seeding is probably the base level. But the issue is we'd like more incorporation, but that's difficult in a direct drilled stubble retained system. Lime's very slow to move, with or without tillage, and it's one of the big issues with liming, is firstly how to get it mixed into the top 10 centimetres and then into the next 20 centimetres. Now that we've thought through and applied those 4 R's as applied to liming, can we move on to the next issue and forget about it? No, well in fact we do know that acidification will continue, particularly in highly productive agricultural situations. The two processes that drive acidification, firstly the removal of cations, such as calcium and magnesium in agricultural products, and secondly that the nitrification of ammonium from fertilisers or from legumes causes the production of a hydrogen ion and a production of nitrate, hence the term nitrification. And that nitrate leaches down the profile and leaves behind the hydrogen in the topsoil, which contributes to acidification. And different nitrogen sources have different acidification potentials. For example, ammonium sulfate would require about 6 kilograms of lime for each kilogram of nitrogen supplied, while for urea, 2 kilograms of lime for each kilogram of nitrogen applied. Potassium nitrate, because the nitrogen's already in the nitrate form, doesn't need to be nitrified, so has no nitrification potential. But of course it is a very expensive form of nitrogen. With the removal of cations, as well as the movement of hydrogen ions deeper into the soil, there's another important aspect, which is the development of acidity in the subsoil. As the acidification proceeds, we might be able to deal with the acidic topsoils with liming. But because lime's not very soluble or mobile, it won't easily move into the subsoil, and I suppose that's the biggest issue at the moment to consider in the acid soil story. How do we address subsoil acidity? At the moment there are no easy solutions, especially in modern no-till systems. Deep ripping or deep banding of lime is a suggestion, but that's an expensive, disruptive and difficult process, and this is a topic of ongoing research. So where does that leave us with soil pH and liming? Well, the first thing to know is the soil pH, both in the topsoil and in the subsoil. It's also important to assess the variability of pH across the paddock and to consider a variable rate lime strategy. We should also be thinking about selecting good quality lime and applying that lime at a rate to get to pH 5.2. Lime's most effective when incorporated in the early autumn because that gives time for the release of carbonates to neutralise the hydrogen ions. Ongoing monitoring is important through regular soil testing, as reliming will almost certainly be needed after 5 to 7 years in the most productive paddocks. And finally, acidification isn't the only issue we might face in a paddock. We've talked specifically about acid soils and the need for liming, but you might also have sodic soils which require gypsum, or saline soils that might have salt in them. In fact, there are all combinations of salinity, acidicity and acidity, both in the topsoil and subsoil, which have slightly different approaches to looking at ameliorating those soil conditions. If you want to find more about those options, you can access the document indicated on the slide that describes these approaches at the Victorian Resources Online website. Thank you.